Okay, now we are entering into Chapter 7. Chapter 7 is about kinetic energy and work. Before we get too far, we need to actually sit down and define energy. Energy is a very broad term. To start with, it is a scalar quantity. There is no direction associated with it. And energy itself is connected in many ways with the state of one or more objects, depending on what the system actually is. Now, when we get a little bit further, we're going to introduce a concept called energy conservation. This is based on one of our fundamental laws. Now, the idea of this fundamental law is that we can neither create nor destroy energy. It has to come from somewhere. So what we can do is we can take energy in one form and transfer it to another form. So energy can be transformed from one type to another, but we can neither create nor destroy energy. So the first type of energy we're going to look at is what we know as kinetic energy. Kinetic energy is an energy that's associated with motion. So an object has to be moving for it to have kinetic energy. Now, how we calculate kinetic energy, obviously we're looking for objects that are fairly large, they're not subatomic, and they're going to be going normal velocities. We're not looking at speed of light. So we calculate kinetic energy as 1/2 mv squared, where m is the mass and v is the velocity of the object. Now this would be the magnitude of the velocity squared, because remember, kinetic energy is a scalar quantity. It does not have a direction. So let's look at an example. Let's say that we have a 3-kilogram duck, and it is going to fly past us at 2 meters per second. When we look for the kinetic energy, first, as always, we write our formula, 1/2 mv squared. We're going to look at inserting those values. So we have 3 kilograms and 2 meters per second quantity squared. So that's going to give us 1/2 times 4 times 3. So that's going to give us 6 joules. Now, a joule is a measure in energy. So 1 joule, which is abbreviated as a capital J since it is a person's name, is 1 kilogram times meter squared per second squared. Now, 1 joule is approximately the energy that it would take to lift a soda can from your desk to your mouth. Just a typical 12-ounce soda can. Okay, let's look at another example from your book. In 1896, in Waco, Texas, William Crush parked 2 locomotives at opposite ends of a 6.4-kilometer track. Now, what he did was he tied the throttles open and allowed them to crash head-on into each other in front of about 300,000 people. Of course, there weren't as many safety rules then as there is today, so there was a lot of debris that flew out and hit people and injured and killed some people. So each locomotive weighed about 1.2 times 10 to the 6th newtons. So that's their force due to gravity. We know how far apart they are. The acceleration of each locomotive is about 0.26 meters per second squared. We want to know what the total kinetic energy was of the system just before the collision. Well, one of the easiest ways to do this is to first find the velocity. So first we need to find the velocity. Now this would be just before the collision. Now what's going to happen is that each of these locomotives is going to travel half of this distance. They have the same acceleration. They're each going to cover 3.2 kilometers before the actual collision takes place. So in order to find the velocity, what we have is we have the initial velocity is 0. We have that the acceleration is 0.26 meters per second squared. And we know that the change in the position is going to be 3.2 kilometers. From that, we could use v squared equals v naught squared plus 2a change in x, because that way we don't have to find a time. We know that the final velocity is going to be the initial velocity, which is 0, plus 2 times 0.26 times 3.2. So what we're going to get is that the initial velocity is going to be the square root of that. So square root of 2 times 3.2 times 0.26, which is going to be about 40.8 meters per second. So once we have the velocity, what are we going to do? Well, once we have the velocity, we're looking for what the kinetic energy is of the system. So the kinetic energy of one of these, is going to equal 1/2 mv squared. Well, what is the mass? The mass, if this is our weight, is 1.2 times 10 to the 6. This is our force due to gravity. That's equal to mass times gravity. So we have to find the mass by dividing 1.2 times 10 to the 6th by 9.8. So let's just be aware of that. So that's going to give us a mass of approximately 1.22 times 10 to the 5th, and that's going to be in kilograms. So just under a factor of 10 difference. So we're going to have 1/2 times our mass, which is the 1.22 times 10 to the 5th, times our velocity, 40.8 quantity squared. And that's going to give us a kinetic energy of about 1 times 10 to the 8th joule. Well, that's just for one of them. We've got 2 of these locomotives coming together. So what we need to stop and realize is that if we have 2 of these, one coming in from the left and one coming in from the right, they're each have the same 1 times 10 to the 8th joules energy. The total energy is going to be 2 times that 1 times 10 to the 8th. So we're going to add their energies. So that's going to give us 2 times 10 to the 8th joules as their total kinetic energy. Okay, so next time we're going to be talking about work and how work ties into kinetic energy. So stay tuned.